For decades, mathematicians have wondered about a type of object that always lands on the same side, but just recently, a team of mathematicians came up with an answer. This all began in 1966 with John Conway and Richard Guy, who came up with a couple rules for the question. First, the object had to be a tetrahedron, meaning having 4 triangular sides. Second, it all had to be made of the same material, with its weight evenly distributed. This object had to be monostable, meaning stable on only one side, so if the object were on any other side, it would always flip over onto the stable one, directly or indirectly. This all relies on a fundamental concept in physics, the center of mass. So, before we get any further into this story, let's review the basics of that. The center of mass of the monostable tetrahedron had to be in a very specific part of the structure, a part which itself would be a small inner tetrahedron. Centers of mass for 3-dimensional objects like this are complex, so let's first go over how it works in lower dimensions. First, 1-dimensional objects. If they all have equal weight, we, as you might expect, just take the average position of the objects, add the location for each one, measured as a distance from the origin, an arbitrary starting point, and divide by the total number of objects. If the objects are differently weighted, we, weigh them differently in the calculation by multiplying objects' distances by their masses. In the second dimension, you do the same type of calculations, except you do them twice to get both the x and the y coordinates. Similarly, in the third dimension, the one our world is in, we do that kind of calculation 3 times. You may notice that this process, especially in summation notation, seems similar to integration, and that's exactly a method used for calculating centers of mass. This also gets more complex in higher dimensions. For instance, in the third dimension, we use third integrals of density functions, functions that output the local density at a given position. We use these more complex density functions because the real world isn't as nice and neat as the small amount of separate objects you might find in models like these. This makes it more interesting to calculate centers of mass for objects like this monostable tetrahedron. Now, back to those 2 rules. At least, they were the rules until Conway and Guy proved that satisfying both of them was impossible, so they took out the second one. Conway thought that a monostable tetrahedron was indeed possible, and while he did not prove this a couple years ago, some other mathematicians did. Professor Gabor Domokos, his graduate students Gerger Almadi and Christina Regers, plus another professor, Robert Dawson. Actually building the thing proved more difficult, especially because acquiring arbitrarily light or dense material can get quite expensive, if not impossible, and yet the team, with the help of a precision engineering company, published a working model just this June. While this may all just seem like pure theory, this monostable tetrahedron has important applications, like for designing spacecrafts that end up on the right side on, for example, the moon. This research is a great example of how people in STEM fields are discovering amazing things, and NSTEM works to empower that expertise in future generations will push progress on questions like these even further. Contribute to this mission by starting an NSTEM chapter at your school or becoming an individual global member today.